Okay, let's talk about the differential form of conservation of mass, and that is our continuity equation. So where does it come from? Well, what you do in order to come up with our conservation of mass is to do the same thing you do anytime you want to get a differential equation for whatever concept you're doing in engineering. It's the same process for everything. And what that is take a little chunk out of whatever it is you're looking at, and for fluid mechanics, well, that's a flow. So take a little chunk out of the middle of your pipe or whatever flowing you have, and so this little chunk is actually a differential chunk. So if this is x, this is dx, this is dy, and this length would be dz coming out of the page. Okay, so if we're doing conservation of mass, we're going to look at mass flowing through all of those edges of all that mini control volume. So for instance, we would have an m dot x in, we would call it, coming in this face, and this face happens to have area of dy dz. Okay, and then this would be our m dot m. Okay, pen's not working. M dot x out. Okay, and the key to all these problems is when it's just a little differential area like that, that it's going through, or a differential distance from here to here, the only thing it can really do is change linearly. It's not going to be able to do some sort of parabolic change in between that very, very small area. So y equals mx plus b, well, that m is your slope, that's a derivative. Okay, so we can say our m dot x out is approximately equal to m dot x in, or intercept, plus dm dot dx, being a partial, times dx, that distance across that we're going. Okay, so it's just got to be changing linearly when it's that small. And that is key. Okay, and that's how you derive all of these kind of equations. So you'll see this again in other classes. You'll see it in heat transfer, I think in dynamics, and all over the place. So just remember that. That's the thing to remember about this is what you do. You make just a linear change from there to there. And then you start plugging in. Okay, so for us, our conservation of mass for control volume, big or little, is this equation that we had before. Well, our m dots are just rho VA, and if our CV is small, this kind of thing here, we're not going to have rho changing all over that little volume. It's going to be at a point. So rho basically is going to be a constant with respect to v, and so you could pull it out of that integral, and so our ddt term with that triple integral is just going to go to d rho dt. Once we pull the rho out, the integral of dv is just v. Okay, but our v for this little tiny control volume is just dx times dy times dz. All right, and we also know that our m dot, our equation for m dot, is rho times v times a, where v is velocity. So our m dot x is going to be rho times u times our a is dy dz, like I said before. Okay, so take that, plug it in to our outs and our ins, and also with that key that I wrote on the previous page, and I'm not going to go through all those steps, but plug that in and divide by dx dy dz. What you end up with is d rho dt plus d rho u dx plus d, these are partial derivatives, of rho v with respect to y plus the partial of rho w with respect to z. Okay, that is your general continuity equation or conservation of mass. Okay, with some of the steps in between here missing, but that's okay. Just remember that what I said before about the linear change in such a small distance. Okay, so special cases, just like we've done before in our control volume analysis, steady flow. If you have steady flow, any ddt term goes away, so what we're left with is just are these other terms, d rho u dx plus d rho v dy plus d rho w dz. And if it's incompressible, that means rho in all of these can come out of your derivative. Well, if rho isn't changing, if it's constant, it can't change in time. So that first term goes away, whether it's steady or unsteady. Then our rho's come out as well, so out of this thing. So well, let me just write this. d rho dt is going to be 0. And then rho comes out here, and you get du dx, rho dv dy, plus rho dw dz equals, oops, I forgot my equals 0 up here, equals 0. Okay, so if we get rid of that, then we have rho's in each one of these terms and 0 on the other side, so we can cancel it out. And our continuity equation for incompressible is steady or unsteady is du dx plus dv dy plus dw dz equals 0. And it's steady or unsteady because the rho can't change. If it's constant, it can't change in time. So that term goes away, steady or unsteady. All right, so cylindrical coordinates then, you would go through that same process that we just kind of went through, doing a mini control volume and then looking at all the sides and how's the mass flow through with it. The only difference is we have different coordinates here, so something weird going on with that picture, but you should have the right thing in your notes. This should be z, this should be r, and this should be theta going around here. Those are our coordinates, and if you look at our velocities, we got a vz is the axial component, vr is the radial component, and then a v theta going around, or kind of our circular component of velocity. And if you go ahead and make a little pie shape instead of a cube for your little tiny control volume, differential control volume, here you have a d theta, this would be your dr, and across here it's going to be r d theta. Okay, and we're going to have a dz kind of coming out of the page here. If you do that, do control conservation of mass on that whole thing, what you get is this as a general form. If it's steady, again, we can drop that d rho dt, and it just becomes 1 over r ddr of r rho vr plus 1 over r dd theta of r v theta plus ddz of rho vz equals 0. Okay, and if it's incompressible, again, we can pull the rho's out of all these derivatives, divide through, and the rho's just go away. 1 over r ddr of rvr plus 1 over r dd theta of v theta, so just dv theta d theta, plus dvz dz equals 0. Okay, this little term here, the RVR, is a little bit weird, but all you need to do is remember to multiply by your VR by R before you take the derivative. Okay, don't try to cancel this R with this R, they don't cancel. Let me write that down, that's a very common mistake. These R's don't cancel because one's inside the derivative and one's outside, so you can't just cancel them, and they are variables, they're not constants. Okay, so let's do a little example here. So again, like our stagnation point, we're given velocities. This, by the way, is not this cylindrical coordinates. We'll have another example with cylindrical. This is back to Cartesian coordinates. So steady incompressible flow, measurements give a U of this equation, a V of this equation, A and C are constants, W is that equation. Okay, is this valid? Okay, so by valid, what we mean is, does it satisfy conservation of mass? It has to, or else something's all wrong. Okay, so does continuity work? So that's what we're going to do. Check if satisfies continuity. So if we do this stuff up here, if it doesn't come out to be 0, then it does not satisfy continuity. So that's what we need to do. So let's look. This is not cylindrical coordinates. This was go back to your regular rectangular coordinates, du dx plus dv dy plus dw dz equals 0 for steady incompressible, right? That's actually for any incompressible. Okay, so, well, du dx, we can find that. Let's look at this. So when you do du dx, remember, if you're doing a partial, just treat any other variable as if it's a constant. So we have an ax squared y term, so that's going to give you 2axy, okay? Because the a and the y are going to be treated like constants, okay? And then we have a plus ay cubed. Well, there's no x in that term, so that's like a constant, so the derivative of that would be 0. Okay, so our dv dy term then, let's do that one. Well, we've got a y in here, so that's going to be equal to minus a, let me put that 2 from our derivative of y squared, 2ayx. The x and the a stay because we're treating them like constants, remember? And then the last term, dw dz, well, derivative of a constant is just 0. Okay, so let's plug these into our continuity equation. And so what you get is 2axy, and then plus our dv dy minus 2axy, and then plus 0. Does that equal 0? Yes, it does. Check. So yes, it does satisfy continuity and it's valid. Okay. Another type of problem we can have with this is, so we're given this velocity and we want to find, we're given u and w but not v. We want to use continuity to figure out what v looks like. Okay, so again, rectangular, du dx, and I can tell it's rectangular because I'm given u's and w's, dv dy plus dw dz equals 0. So what we're going to do is plug in and then try to solve for v, okay, because we don't know what v is at this point. So our du dx is just k z squared, okay, plus, well, we better leave dv dy, plus dw dz, well, there is no z in there, so that's 0. Okay, so let's solve for dv dy, and what you want to do is separate the variables. And most of our differential equations are just going to be the easiest kind here, which is separating the variables, just like this. So when you separate the variables, what you're going to do is take this term over to the other side and multiply through by dy. So you get dv equals minus kz squared dy, right? And now just take the integral of both sides. The separation of variables is easy. So if you take the integral of both sides, what you get on this left-hand side is v. And what you get on the right-hand side, well, there's no y in here, so you're going to have a minus kz squared y when you take that integral. And don't forget, normally when you have an integral, you're going to put in a constant of integration. But when it's an integral with partials like this, it's not just a constant of integration, it's actually a function of every other variable you weren't integrating with respect to. So we were integrating with respect to y, so we know there's no y in this function, but there could be an x, a z, or a t. Okay? So that is our answer. And we know that it's not just a constant, that it's a whole function out here, because if you took the partial with respect to y of this, you would get a 0, whether it's a constant or whether it has z's or x's or t's in it, because you're treating, when you do partials, you're treating those other variables like they're constants. Okay, last example before I let you go do the quiz here. Incompressible flow, and this is our cylindrical coordinates, given VR here and a VZ equals 0, A is a constant. Find the form of the theta velocity. Okay, so we're going to do the same process. Don't let these v thetas and VRs and all that confuse you. It's the same process every time. We're just going to start with the cylindrical form of the continuity equation. And for incompressible, that is going to be 1 over r ddr of RVR plus, where that little r, that's a subscript, 1 over r dv theta d theta plus dvz dz equals 0. Okay, well, if vz equals 0, this term goes away. And if that term goes away, let's multiply through by r. So those 1 over r's go away. And so what we're going to need here is the derivative of RVR. So like I said, what you do for that is go ahead and multiply RVR by r before you take the derivative. Okay, so RVR, so the derivative of RVR is the derivative of A, and then it's just going to be over r instead of over r squared, right? Because we're multiplying by r. So that is going to be A, and I'm going to write this r to the minus 1. Okay, so when you put it as exponents like that, it's easier to take the derivative. Okay, times cosine theta. Okay, and then plus dv theta. We don't know what that is. That's what we're trying to find. D theta equals 0. Okay, so we can find the derivative of this. It's just, we're going to remember treat cosine theta as a constant because we're treating theta as a constant for the partial. A is a constant. So we're going to get A cosine theta, and then the derivative of r to the minus 1 is minus r to the minus 2, right? So we're going to end up with A over r squared cosine theta equals dv theta d theta, or not equals, plus dv theta d theta equals 0. Okay, and again, separate the variables, and what you get then is dv theta equals minus a over r squared cosine theta d theta. Okay, when you take the integral of that, okay, the a is going to pop out, and remember this is d theta, so now we're going to treat the r as a constant, pull it out, and we just have to integrate cosine theta, and the integral of that is going to be our sine theta. So our I lost my minus sign here when I took the derivative. Minus sign. So this is a plus. Okay. Okay, good. We're all good now. So integral of dv theta is v theta, and the integral here on the right-hand side is going to be a over r squared sine theta. And then let's not forget, where we normally would put in a constant integration, we're going to put in a function of all the non-theta variables here. So that would be r, z, t. Okay, and that is our answer. Okay. So stop here and do quiz questions 3 and 4.